sitters, good morning to those who've just joined us. You're hanging out with Looney and we're doing prelim exam review. So as I said in the math show, we're running the last lap, guys. This is the final race now, and as you know, we're always with you, going the distance with you, holding your hand throughout the way. And with that said, we do have a Learn Extra exam revision marathon competition. Very long name for that competition, but that's the competition that we're running. We do have our prizes sponsored by Samsung. You can win yourself an awesome tablet, guys. All you need to do is download the notes today. Download your notes, and right at the bottom you'll see your race number. Keep that, guys, because entry is open on Monday. Okay, so keep that race number, and entries will open on Monday to enter yourself into the competition to stand a chance to win that awesome tablet. But for those of you who do have a Samsung tablet or a premium smartphone, you can simply go on to, let me just show you quickly. This is the library from the Learning Hub, right? So what you need to do is just check out all the exam revision content that we have on the Learning Hub from Samsung. You go onto the stores if you don't have it, and you press on brands, Mindset Learn, and you'll see there that we have all the great exam revision content from Learn Extra, and it's updated on a daily basis, guys, so you can buy yourself all that cool content. Remember, for your smartphone, you search for learning under Samsung Hub, and for your tablets, you check for the Learning Hub under the Samsung apps. Okay, guys, remember, entry is open on Monday if you don't have a smartphone or a Samsung tablet, guys, to stand yourself a chance to win that great tablet. So all you need to do, download the notes and then keep your race number at the bottom. I will post the notes on facebook.com/learnextra. I'm speaking like I don't have somebody in studio with me, so I will go pay attention to that lovely lady. Hello, Tracy.
Fine, you don't want to pay me attention. It's okay.
How are you?
Good, and you?
I'm good, thank you. What are we doing for the mindsetters today?
Well, prelim review. So
Yes.
we did some on Tuesday, and
Okay.
today we're going to do a couple of the other questions that they might have struggled with during the exams.
All right,
Yeah.
grade 12s, you heard it. We always got your back here on Learn Extra. So make sure that you tuned in. You've got your notepads, and you're writing down all the notes. I will post the notes on Facebook. Remember, our page is facebook.com/Learn Extra. Our Twitter handle is @LearnExtra, and you can download the notes on learnextra.co.za/live. I've been talking forever, so I'll take it straight back to Tracy.
Okay, well, guys, today we're going to look at particularly the GDE exam. Okay, so it's the Gauteng prelim. If you wrote it, that's great. Hopefully you've done some revision of that over this last week. If you didn't, even better, because now you see it for the first time. These are really good questions. So we're going to look at a little bit of mechanics, a little bit of work, energy, and power, a little bit of electricity, which we know we all hate. It's one of my favorites, but that's besides the point. So we're going to jump straight in, and the first question we're going to do, if the machine doesn't do its own thing, is we're going to look at the mechanics question, which was the equations of motion question. Now, it said to us that a weather balloon with an electronic sensor of mass 35 grams. So the first thing we need to do, of course, is we need to make sure we know what the important information is. So we have something with a mass of 35 grams, moves vertically upwards with a velocity of 3 meters per second. So it's going up, and we have a velocity of 3. At a height of 150, the sensor breaks free from the balloon and falls to the ground as shown in the diagram. Ignore the effects of air friction. So basically what you need to recognize is the sensor breaks free, which means that the sensor is going to go up and then come back down. That's essentially the sensor's direction of motion. The sensor is going to have a displacement here of 150 from the balloon, and the initial velocity is going to be 3 meters per second up. Okay, for the sensor. I'm not concerned about the balloon right now. First thing they ask you to draw is draw a free labeled body diagram. Sorry, draw a labeled free body diagram showing the forces or forces acting on the sensor while it falls. Now, this was a very interesting question to mark when I marked this with my learners, because they put force or forces, you automatically think there has to be more than one. It was a distractor. Look at the mark allocation. It's only 1 mark. Okay? Generally, if there's more than one force, they're going to give you more than 1 mark. The only force acting on that sensor once it's dropped from the balloon is gravity. I know it goes up first, but that's because its initial velocity was from the balloon. So initially it is going up, but once it's left the balloon, it's no longer in contact with the weather balloon, the only force acting on it is gravity. So what they wanted was just this. FG, weight, force of gravity, force of the earth on the balloon, any of those labels, okay? That was it. Any extra forces on that, you didn't get any marks, okay? Now they say, calculate the magnitude and direction of the velocity at which the sensor reaches the ground. First of all, direction is easy because we realize it's going to be going down. Okay, it was up in the air, now it's falling to the ground, it's going downwards. Okay, so that's easy. What is important in this section is you've got to choose a direction as positive. Now, depending on how you've been taught this direction, you can either choose up as positive or down as positive. When I do these, I like to say, rather than learning that down is always positive or up is always positive, because that doesn't always work, because sometimes you have things that are only moving up, sometimes you have things that are only moving down. I would rather, and this is a personal thing, is you go choose the original direction of motion as positive. Now remember, I drew a little diagram that looked like this. Okay, we said from here to here, that's 150, and my initial velocity was 3 meters per second up. You can do this in one motion. What I'm going to do is, because the sensor was going up originally, I'm going to say up is positive. Next step is to write a list of the information we know, or what we are asked to find. So this is where we go, okay? It's taken from your equations. Now, we're asked to find VF, so VF is my unknown. VI, I've chosen up as positive, so VI is positive 3 meters per second. Acceleration is the acceleration due to gravity, which means it's 9.8 meters per second squared down. Now we've chosen up as positive, which means that is minus 9.8 meters per second squared. And now here's where the confusion happens. Time we don't know, so we're not going to worry about that. But delta y we do know. Be careful here. Delta y is down from the original starting point. So delta y is 150 meters below where we started, which means delta y is minus 150 meters. Okay? Very, very important to get this. The issue with this question is that we're going to have to use the equation v squared equals vi squared plus 2a delta y. Okay? We're going to use this equation. Because of the squares, the negatives tend to cancel each other out. So if you forget to put in negatives along the way, often it doesn't make a difference to the answer, but you still don't get the marks because your method is incorrect. Okay? So VF squared is what I'm looking for. VI is 3. We have minus 9.8 minus 150. Okay? And I'm not going to do all the maths because we've just had a maths lesson. I think you guys can manage that. And we get 54.3 meters per second. Because I would have squared it, I know, okay, straight away that this is going to have to be downwards. I'm not going to get a negative answer because I've got a positive value to square. Okay? 54.3 meters per second down. Please be careful with direction. Very, 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 very important. This is very important for the next part of this question. We have chosen up as positive. You cannot, in the next part of the question, choose down as positive now. You can't change your sign convention. It's all part of the same question. Okay? So the next part of the question says, sketch a velocity versus time graph for the motion of the sensor from the instant it breaks loose until it reaches the ground. Indicate appropriate velocity values. It is not necessary to show any time values. What are they saying? You need to indicate that your initial velocity was 3 meters per second you need to indicate that your final velocity is actually minus 54,3. Now, I know in the last question I said 54,3 positive, but then I put the direction in words, so we left it as that. But now, because it's on a graph and because we're using that value, it's got to be negative because it's going down. What we also need to recognize here is that the only thing acting on this object was gravity. So the acceleration due to gravity was 9.8 meters per second squared. So it is a straight line with a constant gradient. Okay? So when we draw a graph, and you would do this with a ruler, okay? So you do it nice and neat. So there's my acceleration. There's our axis, so we have to have no, I'm lying to you, we have to have velocity, which is in meters per second. You have to have units. This is time. In seconds, you have to have units, okay? They only wanted two values on it. They wanted the 3 meters per second. Sorry, you don't need to put the units in here, that's 3. And they wanted, and I haven't quite drawn it long enough, but it's okay, the minus 54,3. Okay? So we know we've got to have those two. The next thing we need to recognize is that sorry, I'm using my earpiece along the way, but let's not go there, hey? Anyway, moving on. Okay, we're all sorted. It only went from 3 meters per second to 0 for a very short period of time. It was going down for a much longer period of time. So when I draw in my actual graph, okay, they want to see, and this was in the memo, okay, so it's not quite right, but it'll do, okay. What are they looking for? Is it a straight line? First thing. Will it go through 0? Did it start at 3? Did it end at 54,3? And is this section of the graph longer than the first part of the graph? Very important. Easy 4 marks, but I know when I was marking with my learners, unfortunately, it's also very easy to make very silly mistakes on it, okay? The things we've got to remember is that acceleration didn't change, okay, which means it's a straight line. You're not going to get this as a curve. And it's velocity, not speed, so you can get a negative value, okay? Then they say, without a calculation, write down the magnitude and direction of the physical quantity represented by the gradient of the sketch graph in question 1.3. We've just been saying that the whole time. The gradient is equal to acceleration due to gravity, okay? And they just wanted didn't have to write it all out. All they wanted was what it is equal to. It's equal to A, and it says magnitude, 9.8 meters per second squared. Direction, down. Okay? Acceleration due to gravity, 9.8 meters per second squared down. Now, very likely, if I had to actually work out the gradient of my graph, because it's not accurate, we wouldn't get that, but that doesn't matter. Now, this was an interesting question because here's your relative velocity question. After the sensor breaks loose, the balloon maintains a constant velocity of 3 meters per second upwards. Determine the magnitude and direction of the velocity of the balloon relative to the sensor the instant the sensor reaches the ground. Now, what are you recognizing? The balloon is going up at 3 still. The sensor is coming down at 54,3 meters per second. They are moving away from each other, so they are going to appear to be going faster. So it's actually going to be 57, and it's the balloon relative to the sensor. So if the sensor was watching the balloon is going up while the sensor's going down, okay? So the balloon is going up, but it's getting further away, so the velocity of the balloon is going to be 57,3 meters per second upwards, okay? Now, this was unfortunately done quite badly because I know you don't always get where your relative is, but it's okay. Now it says the direction of the ground relative to the balloon. So now we're in the balloon, okay, as the 0 point, watching the ground, and the balloon's going up at 3 meters per second, so the ground can't be going faster than that, so it's going to be 3, but we're watching the ground as if the ground is moving. The balloon is your 0 point. The ground is moving away from you, so it's 3 meters per second down. Okay, it's all about your point of view. That's what you needed to look at. That was a nasty, nasty question, but it was only worth 4 marks, so hopefully we've got that sorted. And you know what? I've timed that perfectly. So, Looney,
Yes.
it's time for a break.
All right. Mindsetters, we are going to take a very short break. Thank you so much for tuning in. I see a lot of you guys are going, go Tracy, go Tracy, go. So with that said, we are going to take a break and we'll see you straight after this. Welcome back, Mindsetters, from a very short break. You know, sometimes things that happen in my ear. But anyway, Floyd Maudley is asking Tracy,
Yes.
what are the topics on physical sciences paper 1?
Okay, well, Floyd, hopefully you would know this by now because otherwise your prelim might have been a bit scary. But your topics are mechanics, which is equations of motion, work, power, and energy, momentum, all of those sort of things. Then you've got wave, sound, and light, which is 3D diffraction, single slits, all the stuff on light, electromagnetic radiation, all of that sort of stuff. And then you have electricity and magnetism, which is your circuits, your electrostatics and electricity from grade 11, and things like motors and generators and that sort of thing. Yeah.
All right, cool.
Yeah.
And then Karabo Shokane is asking, how do we draw a displacement time graph? Is it similar to that of a position time graph?
Okay, a displacement time graph is a position time graph. Okay, they're exactly the same thing. Now, if we had to draw the displacement time graph for this last question, which they could have asked as well, so actually I'm going to do this as well, is we start with making sure we've got our lines. Now, what we need to remember, okay, is we chose up as positive, okay, and the nice thing about your displacement time graphs is they actually end up looking very similar with vertical motion to the actual motion of the object. So where it started is your 0 point, okay, so this is the displacement time graph or position time graph, and this is time, okay, and they could have asked you this as well if they really wanted to, and what they would have wanted is to recognize that as it goes up, it slows down, then it's going to come back down, go back to original position, and then go all the way back down, and your final position over here would be 150. We don't know what this top position is because they didn't ask you it, okay? They might ask you to sketch this graph, but you couldn't put in values like time. You wouldn't be able to put in values like what the top displacement was because they didn't ask you to calculate it. Okay, so the nice thing is it looks very similar to the actual motion, which is actually very cool. Okay.
We have another question,
yes.
sorry, but it's on that, so I
Yes.
just quickly want to ask it. It's from Matsoba Netefo and is asking, I'll try to read it as he says it, I hope you understand. I didn't pass well, why is the vertical displacement negative? If I chose up as negative, the displacement would the displacement vertically be positive?
Yes. If you chose up as negative, it means you chose down as positive, okay? Which then means that when you look at your substitution over here, okay, so say you chose up as positive, up as negative, which means you chose down as positive, okay? So if you chose down as positive, it would mean that you would need a negative in the -3, and those both become positive values, and then you get the same answer. But you have to have the negative there. So you're welcome to do that. There really is nothing wrong with that. There's no reason why you can't choose. Either way, it's up to you, but you've got to make sure the substitution is correct. Okay.
All right, thank you.
So let's go on to the next question, which was from question 4, and it says the diagram below shows a stationary trolley of mass 5 kilograms. So this trolley over here isn't going anywhere. On a horizontal surface at point Y, a steel ball of mass 6 kilograms is projected up the slope. At point X, the steel ball has a velocity of 8. Great, it's all written there. The steel ball collides with the trolley at Y, so it gets to this point, there's a collision, and ignore the effects of friction. Brilliant. Now, immediately after the collision, the trolley, so the collision happens, okay, so I'm going to do it here. Ball and trolley, we know I can't draw. The trolley has a velocity of 1.5 meters per second to the right, and the steel ball is now going in the opposite direction, which means it's actually going to go back down the slope of 0.5 meters per second. Calculate the velocity of the steel ball just before impact. In other words, what is the velocity of the steel ball over there? Okay? There was a collision, which means this is a momentum question, so we're going to use momentum. Okay, so straight away, we go total momentum before equals total momentum afterwards. Okay, and we have two objects that are, and I'm writing nonsense over there, two objects that are separate before and they are separate afterwards. Okay, what I know is the steel ball, whose mass was is 6 kilograms. Before the collision, we don't know what its velocity is. They didn't tell us. It collides with a trolley whose mass is 5 kilograms, but not going anywhere. Now, what I haven't done actually is I haven't actually decided which direction is positive. So I'm going to go to the right is positive because I know that the steel ball was going to the right to start off with, okay? Afterwards, the steel ball is now going at minus 0.5. The trolley was going at 1.5. Okay, so we're going to get 6. This gives me minus 3. And we'll just quickly work out because my brain's asleep. 5 times 1.5. 7.5. Okay, so that's plus 7.5. And we get 6 for its initial velocity. Minus 3 plus 7.5 is 4.5. And so now we'll go 4.5 divided by 6 is 0.75. Okay? 0.75, it's positive, which is what we expected, to the right. First question, done. Okay, it's a momentum question, nothing difficult about that. So now I'm going to go back to my diagram, and over here, and I've drawn a whole bunch of other stuff, is I'm going to write in that that's 0.75 meters per second. Now, all the stuff I've drawn here, grade 12s, this is what I think your exam paper should look like. Okay? So when you go look at your question paper when you're done, this is what it should look like with all this scribbling on it, because you forget what you've worked out. And the issue is you forget what you've worked out, so when you get to a question later on where they expect you to use it, you can't remember. And you go, I don't know where the information is coming from because you haven't written it down. So make sure you write it down. It'll make your life a lot easier along the way. Now they say to you, state the law of conservation of mechanical energy in words. Definition. There were lots of definitions in the Gauteng prelim. There will be lots of definitions in your final exam. Okay? So state the law of mechanical engineering. Total mechanical energy is conserved in a closed or isolated system. Okay? The total mechanical energy is conserved in a closed or isolated system. Definition. You must learn it. Now they say, use the law of conservation of mechanical energy and calculate the height of the horizontal surface. So now we've got to look at this and we go, okay, they want H. The 5 kilogram trolley helps us nothing, does not do anything to help us calculate that height because it stays on that height the whole time. But the steel ball changes. The steel ball goes from going 8 meters per second to going 0.75, and it goes up the system. So what we recognize is over here, its height is 0. We don't know its height, but we know what its velocity is. So for conservation, for this next section, we're going to say that the mechanical energy at, I think they called it point X, there we go, of X, is going to be equal to the mechanical energy at Y. Okay? Now the mechanical energy at X is going to be the velocity at X plus height X, that's potential. It's going to become the kinetic energy at X plus, and now I can call that height, the potential. Okay? At X, so this is a 6 kilogram, it was going at 8. Height was 0. You must put in the 0. Here, this is 6. We worked this out. It was 0.75 squared. That's 6. That's 9.8. We want H. Okay? Sorry, I'm just making sure I get the right answer. Okay? Guys, my biggest issue here was the substitution, because it was about recognizing what information you had. And if you don't write in all the stuff over here, how are you going to remember? Okay? Now it's a math problem. So we go all the way back here, and what I'm going to do is I'm actually going to change the mode of my calculator because I'm tired of the maths display, and that's okay, the maths teachers can use that. 0.5 times 6 times 8 squared, and it's 192. So this is 192 plus 0. Then I've got, and I actually can't do the next one in my head, 0.5 times 6 times 0.7 squared, and that's 1,6875 plus, and now we're going to go 6 times 9.8, 58,8 times height. Now it's just a maths problem. I take the 1,98, the 192, sorry, minus 1.6875, okay, and I'm going to divide it by 58.8, and we get 3,24, okay, because we're rounding off. .24 meters. This really wasn't so bad, but it's just about knowing what information that you need to substitute in, because that information is important. Then the last question, it says, explain in words what is meant by an elastic collision. Seems like a bit of an arbitrary question here, but it comes down to energy. And remember that in an elastic collision, kinetic energy is conserved. So that means that the total kinetic energy before the collision is equal to the total kinetic energy after. You can't use the word mechanical, you can't use the word potential, and you can't just use energy. It is very specifically kinetic energy. And remember, elastic collisions are extremely, extremely rare, because we often get kinetic energy not being conserved because the kinetic energy gets transferred and it becomes things like sound. Maybe if it's two metals, becomes heat, light, becomes heat through friction, all of those sort of things, all right? So it's really important. But the thing I want you to get here is the biggest mistake made in this question was the substitution of that 0.75, because you're not writing down what you're given and what you've worked out. So being able to keep looking at this will definitely help you. It's very, very important. I promise you, you are going to get a momentum question, and you're going to get something to do with energy, whether it be proving elastic collision or not, or whether it be this whole thing of mechanical energy, you're going to get that type of question. Okay, so Luni, I know it's a little early, but I think it's time for a break, unless there's some questions coming in.
Yes, can you just...
Yes, let's do those quickly.
Let's take 2.
Yeah.
Hey, Tracy, what's the relationship between work net and potential energy? That's from Wilfred Kays.
Okay. Work net and potential energy, it's a difficult one. If there's no change in kinetic energy, then the network done by gravity would be equal to your change in potential, but those are very rare questions. We rather work with, and we're going to do in the next question, that work net equals change in kinetic.
Okay, cool.
Yeah.
And then Tamsang Azondo is asking, will the acceleration time graph of an object projected vertically upwards differ from the one of the object projected vertically downwards?
No. It depends on which value you've decided as positive or negative. It's still a straight line, because whether it's projected upwards or downwards, acceleration due to gravity is 9.8 meters per second squared. Done. Always.
All right. Okay, cool. Mindsetters, let's take a very short break and we'll see you straight after this. Welcome back, Mindsetters, from my break. I can see on Facebook you guys are enjoying the show. Shout out to Christoph, Shane, Gabelo, Wilfred, and a special shout out to Api, where you're only in grade 10 and you're watching. Well done to you, thanks. And you even asked how many days before the finals and all of that. Dedicated student you are. 2 more years and you'll be in this seat running the race with us as well to your finals. So well done to you, Afiwe. Tracy.
Oh, my turn. Wow, that didn't take long. Okay, so now we get to the section that we know we all love so much. The work energy theorem question, okay? You are going to get something to do with work energy and the work energy theorem and all those sort of things, so pay attention. So they say to us, a cable is used to lift a steel beam of mass 115 kilograms as shown in diagram A. So this is 115 kilograms. The cable breaks, the beam falls to the ground and gets stuck in soft wet soil as shown in diagram B. So this is the soil, okay, and that is the beam. That's what they're saying. All right, we're not too concerned about the fact that it sort of went at an angle. First thing they ask is state the work energy theorem in words. Now they're trying to lead you here, okay? And remember that the net work done on an object is equal to the object's change in kinetic energy. The net work done on an object is equal to the object's change in kinetic energy. You have to have net work, okay? The net part is really important because we're looking at the net forces involved. Now, the end of the beam hits the ground first with a velocity of 22 meters per second. This end penetrates the ground to a depth of 0.8 meters. Now it says use the work energy theorem and calculate the magnitude of the net force exerted on the beam in order to stop it when it hits the ground. What you need to recognize, this is initial velocity. We're going to stop, which means final velocity is 0. Okay? No, to the 1. Next thing we need to recognize is the beam comes into the soil like this, which means the force needed to stop the beam acts, not like that, acts upwards. That's F net. Okay? F net is acting at an angle of 180 degrees. Biggest mistake here. The beam is moving this way. We need to stop it. So the force acting on the beam opposes the beam's motion and is at 180 degrees. Okay? The only thing we need to look at is the change in kinetic energy. So we say here that net work equals to change in kinetic energy, change in K or change in EK, whichever you've learned, okay? Net work is F net delta X cos theta, and this is going to be final minus initial. Changing anything is always final minus initial. So it's final kinetic energy minus initial kinetic energy. So it's final velocity minus initial velocity, okay? Obviously from here, grade 12s, if your maths is really good and you want to take out a half m as your common factor or anything like that, really, that's fine. It's your choice, doesn't matter. Now we need to do the substitution. F net. Delta x is the depth that it penetrates to, 0.8. Okay? Cos 180 degrees. Okay? My final, and the beam was how many kilograms? It was ridiculous, it was 115. Okay? My final is 0. My initial was 22. So what does that mean here? We actually have 180 cos is minus 1. So this is minus 0.8 F net equal to minus 100, half times 115 times 0 squared is still 0. Okay. And our other part, which is a half times 115 times 22 squared, 27,830. Ooh, come on. Really? There we go. And now we divide by 0.8. Divided by 0.8. 34787,5. And now my earpiece has decided to fall out completely. I love it. Okay. No, I'm writing it down wrong. 34787,5 newtons. Okay, and all they asked for was the magnitude, so you didn't have to give direction. Guys, this is so, so important. If you put cos 0, you would have ended up with negative 34787. You don't get your marks for that, guys. This is really important that you get this. It had to be 180, and you had to go 0 minus 22. Now, what I saw quite often is the 0 there, and then 22 minus 0. You've got everything the wrong way round. So the direction is still important. Even though I didn't want direction in your final answer, it's still got to be part of the way you work it out, okay? So you get 34787,5. You can put it into scientific notation if you really want to, though I would just leave it as that. Okay. Then they say, if the ground was hard and dry at the time of the accident, how would the net force calculated in 3.2 change? Right, increase, decrease, or stays the same? Explain your answer by referring to time, impulse, and net force. Now watch here. If the ground is hard, the total time will decrease, okay, but, okay, impulse is constant because impulse equals your change in momentum. Now, whether it takes 10 seconds, 20 seconds, half a second doesn't make a difference. The impulse is the same, which means if time decreases, then your net force is going to increase. So that increases. Really, really important. I see this all the time, is in your heads, because you recognize, you know the force is going to get bigger, you seem to think that that means the impulse gets bigger or the momentum gets bigger, but it doesn't. That stays the same. The force gets bigger because it has to get to the same answer every time, which means time gets smaller. Okay, very, 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 very important. All right. And now we can move on to circuits. Are there any questions coming through about this section? No, they're all very quiet. I think they're all a little scared. Okay, so next question, because we've got a little bit of time, we can start this now. the circuit diagram below shows how an uncharged capacitor, this is the capacitor, this part here, okay, can maybe charged. The resistor R is used to protect the meter. In other words, the resistor is there to make sure we don't blow up the meters, the ammeter, okay? The switch S is closed. There's my switch S. And the readings on the ammeter and voltmeter are noted. Brilliant. Very unexciting experiment. How does the value on the ammeter change while the capacitor is being charged? And they say to you here, only write increase, decrease, or stay the same. Now, we all know, because we hate capacitors, sorry, I'm just getting my notes, okay, that it becomes quite an interesting little moment here. But this is grade 11 work, so some of you are probably going, I've never seen this in my life before. You have, you saw it in grade 11. What you need to recognize is when we charge a capacitor, the electrons come along, and as the capacitor gets charged, it gains and gains electrons, or whatever the case may be. But as it starts to gain the electrons, fewer and fewer electrons can go onto the capacitor, which means the current gets smaller. So the first question is, how does the value on the reading ammeter change? It decreases. It gets smaller and smaller as the capacitor gets charged. Then they say, how does the value of the reading on the voltmeter change as the capacitor is being charged? Well, the voltmeter is over the capacitor. Remember, capacitance is Q divided by V. Capacitance is a constant. Q is getting bigger, which means V must be getting bigger. So this decreases while V increases. Okay, the ammeter reading decreases, the voltmeter reading increases until it gets to its maximum, until it's completely charged. Okay? Now, the capacitance of the capacitor is 1,5 times 10 to the minus 6 farads, which is actually quite a big capacitor, by the way. And the potential difference across the voltmeter is 21 volts, so this capacitance is let's get rid of that, 1,5 times 10 to the minus 6 farads. The distance between the plates is 3 times 10 to the minus 6 meters. The space between the plates is filled with air. They tell you it's filled with air because if you remember correctly, when you did capacitance in grade 11, you learnt about dielectrics. Now, dielectrics can be things like air, glass, water, plastic, whatever, which then helps with the capacitance. In grade 12, they tend to stick to air because then you don't need to know the constant. So you don't need to worry about the constant that goes with that, okay? And they ask you to calculate the amount of charge stored on the capacitor. And you look at this and you go, well, I just did the equation, which is really nice. And the equation is C equals Q divided by V. Capacitance, we know, 1,5 times 10 to the minus 6. They want Q. We know that that's 21. So it becomes 21 times 1,5. Okay, so watch. We got 21 times 1.5 to the minus 6. And we get 3,15 times 10 to the minus 15. 3 times 10 to the minus 5, sorry. Coulombs. Nice and easy. Now comes the fun question. Calculate the plate area of this capacitor. This is where you need to understand what your information sheet is telling you. We use capacitance, epsilon 0, A divided by D. If we had something other than air, then we would have to add that dielectric constant in, but we don't, so it's great. Straight substitution. This is 1,5 times 10 to the minus 6. Epsilon 0 is a constant given to you on your information sheet. And we want A. The distance was 3 times 10 to the minus 6. Okay. We're going to you take the 3 times 10 to the minus 6 over, divide by 8,85. I'm not going to do the maths. I think you guys can manage that one. 0,51 meters squared. that's actually a really, really big capacitor. But remember, what a capacitor does is, so 0.5 meters squared is fairly large. It's like having a plate like this, and then they wind it up into a circle, well, into a cylinder. And by twisting it on itself, they can actually have the area of the plate bigger, because the greater the area of the plate, the bigger the capacitance. The closer together we can get the plates, the bigger the capacitance. Okay, and the bigger the capacitance, the greater the amount of charge it can store, which is actually really, really, really important. There is 2 more questions to this, but I think we'll leave those, Looney, and we'll do them after the break.
Okay, cool.
Okay.
Mindsetters, we are going to take a very short break. I see some of you guys have questions, so I'll ask Tracy during the break and we'll go through them. But for now, let's take a break and we'll see you straight after this. Welcome back, Mindsetters, from that break. Just a reminder, guys, if we don't get to your questions during the show, we do have a help desk, okay? So all you need to do is go onto learnextra.co.za/helpdesk. Post your questions there, and a teacher will answer you as soon as they can, but it's always immediate, guys, so don't sweat it. And if you have Mixit, those of you who still mix and chat to your friends on Mixit, you can go to the general store on Mixit and get the help desk on your Mixit, okay? It is there, so you get it from your Mixit and then you send your question and then you will be answered, guys. So remember, if you don't answer you during the show, don't sweat. Help desk is there for a reason and you will be answered. Don't you now say, no, Looney, but they don't answer me. They will answer you, Mindsetters. Don't sweat. We always got your back. So Tracy.
Thank you, Looney. Guys, we really do get your answers, and unfortunately, we can't always do your questions on air because sometimes they're not quite with what you're dealing with, or they're not quite appropriate or whatever. So don't worry, your questions will get answered, I promise. Looney's not telling you lies. You know, she wouldn't do that.
Never,
okay,
ever.
Let's just quickly, we have got a couple of questions that have come in with what I've done the last 2 sections, but what we're going to do is let's quickly finish this question and then I'll get to the questions, okay? So they now say to you that the charge capacitor is removed and used as a source of electrical power, potential energy in a different circuit. So it's used like a battery. Now they say to you, state 2 differences in energy transfer in a charge capacitor and that in a battery. Guys, please be careful here, is that I'm not asking how the energy is stored, I'm asking you how the energy is transferred. So the energy is stored, what happens when we transfer it? Now what they wanted is that in a capacitor, the energy gets transferred immediately, it's instantaneous, and all of it gets transferred at once, the whole thing. So once it's transferred its energy, it has nothing left, and it's immediate, it's quick, 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 quick. In a battery, it transfers its energy over time, and it's not all at once, okay? So it transfers smaller amounts of energy over a long period of time, so it lasts longer. There is a train of thought out there, and this has come up in exams before, that capacitors could become the batteries of the future. Why? Because there's no chemicals in them, they are infinitely rechargeable, they're infinitely recyclable in that point of view, so environmentally they are much, much better for the environment because there are no chemicals in them. The issue at the moment, though, is that they discharge so quickly. So we can store the energy in them, but it's finding a way to get them to discharge less quickly, basically, is the issue, okay? Then they say, state and explain one safety precaution which has to be taken when repairing electronic devices containing capacitors, even when these appliances are switched off. Remember, the capacitor gets charged during the appliance's use. When you've switched it off, okay, that capacitor can still be charged. It is still possible to discharge while you're using it. So the capacitor must be discharged safely before you open up a piece of equipment like a TV or whatever. So that's why you only get electricians to do it, because they can discharge the capacitor before they open it up and make sure that it's safe to actually use it or to open it up and do stuff with it, okay? Otherwise you're going to get one very nasty shock. It's not pretty. Okay, now I know, Looney, you had a couple of questions with the last question we did.
Yes.
Should we go back there quickly?
Yes, please.
Yes.
Let me just scroll down here. Now you see my machine is
Having a bit of a slow moment,
yes.
is it? We get in there, don't worry.
Okay.
And then there's dead air on the TV and people are going, what? Come, Looney, hurry up.
Okay, can you just continue? I'll tell you when it's participating.
Well, I do know, Looney was just saying she'll get back.
Question 3.2, I remember it's question 3.2. How did you get 100?
Okay.
Yeah, those.
This is
180
really
degrees.
important, guys. This has come up a lot. You've got to look at the direction that the object's moving at and the direction of the force, okay? And the beam is penetrating the ground downwards, but the beam has to stop. So there's a force from the ground that has to go up. That's at 180 degrees. Remember, 180 degrees is in the opposite direction. So if it's in the opposite direction, that's why theta is 180. If I made theta 0, it would mean that I've got a force that's going in the same direction as the beam. That won't stop the beam. That'll actually make the beam go faster. Okay, so 180 degrees, it's the same as if it was friction. It's in the opposite direction. It's opposing the motion of the beam. Okay, very, very important.
Okay.
Yeah.
And then, nongonyana, I think it's related to what you just said.
Mm-hmm.
Why is W net equals to F net times cos 180?
Well, it's just what I said, okay?
Okay.
It's the whole thing of the 180, whoops, and I've just got the calculator out at the same time. The 180 is because it's in the opposite direction.
Okay.
Okay, because it's opposing the motion.
Okay.
Okay.
And then, when do we put 0 as an angle? That's under again.
Okay, because it's got to be in the same direction. Okay, so the force and the motion are in the same direction, then theta is 0.
Okay.
Okay.
And then, I'm just checking the questions. Or can you take any questions now? Because I was just checking questions that are related to that.
Yeah. Well, we're probably going to have a little bit of time to do any questions
Okay.
just now.
Okay.
We're going to go into some electricity.
Okay. Just
Yeah.
quickly. Motsepana Daniel, what do you mean about the term effective resistance?
Okay, we're going to get to that.
Okay, okay.
Effective resistance means total. So
Okay.
we're going to do electricity now. Okay, so the next question we're actually looking at is the circuit diagram. So you sort of jumped the gun there a little bit, sweetie, but that's okay.
Okay.
I personally love electricity. I get very excited. My kids look at me funny. I love electricity. It's so much fun. Anyway, so the circuit alongside, which in this case is below, consists of a battery of EMF 22 volts, which is written in there, an internal resistance of R. We don't like it. It's okay. Two resistances having resistance of 14 and 28, as well as R1 of unknown resistance. Now, remember what I like to do is I take out my highlighters. Oh, wrong way around. And there's my highlighters. And we go fine. And I'm going to use yellow to start off with. And then everything that's in yellow is in series. I know that the switch isn't closed. It doesn't matter. Gets to that part. Gets over here. And then the circuit splits. So now we get some that's going to be in green. And let's use blue, because they're not the same. Well, I don't know if they're the same. So we have a parallel section, we have a series section, and from there that'll help us along the way. Okay, so now we can go back to this part. Now it says, write down Ohm's law in words. Grade 12s, you have been doing Ohm's law since grade 9, hopefully. You did it in grade 10, you've done it in grade 11, and you're doing it again this year. Okay, so Ohm's law states to us that the resistance, the potential difference across the resistor is directly proportional to the current through the resistor, provided temperature remains constant. It's from the equation R equals V over I. Okay, so the potential difference across the resistor is directly proportional to the current through the resistor as long as temperature remains constant. Have to learn these things. Now they say to us, with switch S1 open and switch S2 closed, what is the reading on V1, V2, and A1? So now we go, if switch S1 is open, you need to recognize that there will be no current in the circuit. Switch S1 is the switch in series. Switch S1 has to be closed for current to flow, which means there will be no reading on V2. V2 will be 0, okay? I'm sorry, my earpiece is determined to fall out today. I'm just going to put it out there, okay? A1 will be 0. V1 will not be 0, because V1 is now measuring EMF, because V1 measures the voltage anyway. So when we go here, V1 would be equal to 22 volts, it's EMF. V2 is equal to 0. A1, now be careful how you write this, is I1, which is equal to 0. You can't say A1 equals because A1 is a reading on ammeter, but it's, it's a current reading. Okay, very important. Now, same diagram. Both S1 and S2 are now closed, so that means my circuit is fine. V1 now has a reading of 21 volts, so that becomes my external voltage, and V2 has a reading of 7. Okay, now I'm going to do this again in the colors we had, because this was yellow, because I just want you to see. Then I went green, I think, and I am now, and then it was blue. Once again, this is what my question will look like on my answer on my question paper. Exactly like it, with everything that I've written here, okay? Then they ask, what is the potential across R1, and give a reason for your answer. So now we've got to go, okay, look here carefully. The only thing in the circuit is the parallel section. So if I put a voltmeter across this parallel section, it will be equal to the voltage of my external circuit, okay, which is this voltmeter reading when it's closed. So this voltage is 21, okay? That means that across this whole section, if I put a voltmeter here, that would be 21 volts. 7 volts, has been used in V2. That leaves me how many for R1? 14. Okay, gives me 14 volts. Now, giving a reason for your answer becomes quite difficult here, because they want you to write it instead of showing you a calculation. So the point is the reading over R1 would be 14 volts, and the reason being the 21 volts external voltage, the 21 external voltage will divide proportionally between the 14 ohms and R1. Will divide proportionally. It's a nice word there. You can't say to me divide equally, because it hasn't divided equally. It divides proportionally. And what is that proportionality to? The resistance. Okay? What you now need to recognize is that R1 is going to have a bigger resistance. It's going to be bigger than 14. Okay? It's probably going to be double. Okay? Now, calculate the reading on ammeter A2. Okay. Ammeter A2 has to do with the 28 ohm resistor. Do I know the voltage over that 28 ohm resistor? Absolutely. It's 21 volts. It's the external. That's my V parallel, external voltage. So, I know that my external voltage, which would be my parallel voltage, is 21 volts. I know resistance, which is 28 ohms. So we want what did they call it? I2. And we go, that's okay, we can do this, because R would then be V parallel divided by I2. R is 28, V is 21. So we're going to have 21 divided by 28, and we get 0.75 amps. And I go back to all my scribbles, and I write 0.75 amps. Okay? Really? Not so bad. Okay, now, calculate the internal resistance of the battery. Life gets fun here. They want R. But you know what? This really isn't as bad as it looks, because what I need to calculate little r is I really need to know what I1 is. And we look at the information we've got and we go, okay, there's a couple of ways around this question. We can find A1 if I know R total. So now we're going to ask ourselves a question. I'm actually going to leave these questions with you because it's about time for a break. So I'm going to leave these questions with you. Can I find R total? So that's the first question you've got to ask yourself. Can I actually find R total? If the answer is no, then I've got to be able to find my total current some other way. All right? So then you've got to say to yourself, is there another way to find I total? Okay? Now, those are the questions you have to ask yourself before you can answer this question. So I'm going to leave those with you to mull over in your heads, and we're going to take a short break, and then I'll answer them for you.
All right. Mindset is think carefully about what Tracy has just asked you. Take a short break, and we'll see you straight after this. Welcome back, Mindsetters, from the break. I hope you thought about that question and you'll post your answers that Tracy asked you. I don't know why I'm doing that, but it seems so cool. Anyway, Tracy.
Yeah, we do worry about her, but it's okay. We'll be sending her home soon. Anyway, apparently it's been a long day for Looney and a long week. Anyway, Looney, you had a really good question before the break, before I carry on with the answer.
Okay.
Do you want to ask it?
Yes. So it's from Lerato Malepe. And this person's faceless. I hope it's a she. How did you know that V1 is external voltage?
Okay. So, sweetie, when this is one of those things where V1 is connected over the cells, okay? When there's no current moving through the circuit, V1 has to measure the potential inside the cells. Once the circuit's closed, essentially what V1 is now is measuring is what's happening everywhere else and not what's happening in the cell, which is why I know it's external, okay? Because it's connected to this part of the cell. So it's something you need to learn. If there's no current, then any voltmeter across the battery is measuring EMF. As soon as there's current, it's measuring external voltage, okay? Because of the way it's connected. And hopefully that helps. Now, I asked you before the break whether we can work out R total or not, and then where do we go? Now, the answer to that question is no, we cannot work out R total because I don't know what R1 is. And I guess in some way maybe we could work out what R1 was, but you know what? This question was only worth 5 marks. It's not worth the hassle. So we can't go that way. Okay, let's just get rid of it because we can't do that. Which means there must be another way to calculate I total, and of course there is. Over here, we recognize that we have a parallel section. So if I can work out the current in the top parallel section, I can add it to the 0.75 of the bottom parallel section, and that gives me my total current, okay, because the current gets split. I can work out the current in this top section because I know a resistance and I know a voltage over that resistor. So that actually is really nice. So what I'm going to do is I'm going to work out the current in the top end of my resistor. And let's look at, and this resistor was the 14 ohm. And that's going to be V2 times I, divided by I, sorry. So this is 14, this is 7. So that I becomes 0.5 amps. So that means this is 0.5 amps over here. So my total is actually 1.25 amps, okay? Because what we're doing is trying to find internal resistance. I'm going to show you why in a second, where I'm going. Okay, and so that becomes I plus I2, which we worked out earlier. So it's 0.5 plus 0. This was a lot of work for 4 marks, by the way. But I don't think there's any easier way to do it. We wanted internal resistance. Remember, V internal equals I times R. It should be written like that. EMF is equal to your external plus your internal. So this is 22 equal to 21. So internal is 1 volt, okay? So we have 1 equal to 1,25 times little r, and little r equals 0,8 ohms. Lot of work for 4 marks, okay? But that's the way it goes with those ones. Then they gave you a really nice question here. Now they say to you, switch 2 is open, switch 1 is closed. The reading on the voltmeter changes. How does the reading on the voltmeter change? Now, what you need to recognize here is if I open, I get rid of that switch. This is still closed. My current now does that. It's a closed circuit. However, I've taken out a resistor in parallel. Your total resistance has increased. Okay? So I'm going to come back to this part. R total increases. If R total increases, then I decreases. If I decreases, V internal decreases. Okay, because remember V internal is I times little r. Little r is a constant, times by my smaller current, that means V internal decreases, which means V external increases, so my reading on my voltmeter increases. Okay, this, I didn't actually put the mark allocation on this. This was worth 4 marks, and the 4 marks came from 1 saying increases, 1 for saying me R total increases, I decreases, V internal decreases. Okay, that's mean. But grade 12s, they are definitely going to ask you questions about what happens when when readings change, or they add stuff or take stuff away. So you need to learn these things, do more questions. Okay, now we've got about 5.5 minutes left, and I know Looney has a list of questions that you wanted to ask, which are actually really great. I'm glad you're interacting. Hopefully we can actually get through them, though she's looking at like she's lost them along the way.
I'm looking for them while you're talking.
She's looking for them. No, we had this big discussion about that's a good question, that's a bad question.
I've
but
got
I think
them.
she's
I've
got them. Okay,
I've
I see the hand up. Okay.
Yes. So Owen Toka is asking, would a capacitor affect the brightness of a bulb connected in series with it during the charging of a capacitor?
Absolutely, Owen. It's another way of asking the question on what happens to the current. So in the question I asked you, what happens to the current while we charge the capacitor? It's the same thing. Brightness of the bulb is related to current. So the smaller the current, the less bright the bulb glows. So in other words, the bulb would get dimmer and dimmer and dimmer until eventually it switches off. Okay?
Okay.
Yeah.
Oh, and again, a net force can either cause motion or stoppage.
Absolutely. It all depends on the direction of the force. Okay? So if net force is in the same direction as the object's moving, then it causes motion. If it's in the opposite direction, it's going to stop it from moving, like friction or gravity or something like that. Okay?
All right. And then now this is like new questions, or comments. Yes, comment from Gabelo. For the Q, I'll first find I in the series connection and plus it to the 0.75A.
Yes, that was for how to work out the current.
Yes.
You had a question about conservation forces and non-conservative forces.
I'll go to
and we'll find out who it.
There you go.
There we go.
And again, what is the difference between conservative forces and non-conservative forces?
Owen, you are on the ball, my boy.
Owen is a ball.
It's actually a really good question. Conservative and non-conservative forces are the ones where mechanical energy gets conserved. Friction is a non-conservative force because friction takes something like, say, kinetic energy and changes it into something that's not a mechanical energy, like heat or light or sound or something like that, okay? Gravity is considered to be a conservative force because mechanical energy remains constant. So friction is a non-conservative force because we can't conserve our mechanical energy, whereas gravity is a conservative force because we can conserve mechanical energy. Yeah.
And then, under Nongonyana, what is the unit measurement of the rate of flow of charge in a conductor?
Rate of flow of charge is current, Sweet Pea. So rate of flow of charge is another, let me just get to a blank page actually, which I don't have. So let's just do it at the bottom of this one, because I can. because I didn't put any blank pages in. That was a bit stupid. Okay. I equals Q over T. Okay, so rate of flow of charge is current, which means it's measured in amps.
Okay, cool.
Yeah.
And then Sipesi Hlenongos is asking, do we use a rheostat resistor in our calculations?
Not really, sweetie. Because with a rheostat, remember we can have variable resistors. If we're going to have a rheostat in a circuit, the rheostat will be set to a specific value so that we can work out calculations based on that. We sometimes would use a rheostat if we're looking at proving Ohm's law, because we can change the resistance, which means we can change the current in the circuit. But for calculations, we'll have to set it at a specific value for you, and then maybe change the value of the rheostat to get like a question like the last one with what happens when we make it higher or smaller, what happens to voltage, current, that sort of thing.
Okay.
Yeah.
Last question. Tabo Boysholo is asking, what is the difference between change in momentum and the rate of change in momentum?
So glad you got to that one. All right, now, change in momentum is m delta v. Don't ask me why I put it in brackets, so let's just take all the brackets out. So change in momentum is m delta v. Rate of change in momentum means I'm taking this and I'm dividing by delta t, okay? So if I take this away, this has become F net. F net is the rate and change in momentum, okay? Because remember, impulse is F net delta t, which is change in momentum, okay? So rate of change in momentum is net force. It's another way of stating Newton's second law, okay? But it's not the same as change in momentum, it's the rate, okay?
All right.
And I think we've probably run out of time, Looney.
Yeah.
Yeah. So I'm going to have to say goodbye. What we're going to do next week, guys, is we're going to look at the chemistry prelim, okay? And we're going to get some from hopefully some of the other provinces. But we've done lots of physics. Keep going, guys. I will see you next week. And I'm done.
All right. Thank you so much, Tracy, for giving us this lesson. She's always just so clever. You ask her a question, she goes, F net. Okay, anyways. Thank you so much, guys, for tuning in. Happy World Teachers Day, Tracy. And thanks to you for tuning in at home. We will see you same time, same place next week. But from us, it is a goodbye. Stay tuned for Life Sciences. Migs will be in the house. I am out until 3 o'clock. Until then, bye.